Hello everyone. Welcome to this lecture series on electronic spectroscopy. This is lecture number 5. In the last lecture, I had discussed this concept called transition moment integral. Okay, under vibrational core structure of electronic spectra. Okay, so in the last lecture, what we discussed under vibrational core structure is actually called quantum mechanical formulation. Quantum mechanical formulation of Franck-Condon principle. Franck-Condon principle. Okay, so whatever we discussed under transition moment integral in the last lecture, okay, they are actually called as quantum mechanical formulation of Franck-Condon principle. In the last lecture, we had this expression for transition moment integral, which consists of the vibrational overlap integral, that is integral psi v prime, psi v double prime. Okay, this is actually called the vibrational overlap integral. Then we also had the spin integral s prime s double prime. Then we have orbital integral, that is psi e prime mu electronic operator and psi e double prime. Yeah, we had this, right? So last class I told you, for transition moment integral to be not equal to 0, all these three integral must be not equal to 0. Okay, the condition for which this integral to be not equal to 0, right, will give you certain restrictions called orbital selection rules. Similarly, for this integral to be not equal to 0, I told you under spin orbit negligible spin orbit coupling, singlet to singlet transition is allowed, triplet to triplet transition is allowed. Okay, so I gave some information about these things in the last lecture. Now let us focus on this. Then before going to discuss this, let me give some information that we had, which I forgot to say in the last class. What is that? See, this integral, see, in the in the last lecture I had said that, yeah, so this is the one we discussed at the end of last lecture. See, I said that this integral is 0. Okay, but this integral is not equal to 0. Why? What is the reason? Right, we say that this is overlap integral. Okay, but this integral this integral is 0. Why? What is the reason? Yeah, see, what is the reason for these things? Let me discuss here. See, the integral psi e prime s prime, psi e double prime s prime double prime. Okay, you can separate this. I said this integral is 0. Right, actually it consists of two parts. You can separate them. That is psi s prime. I'll separate the spin part from the orbital part. Okay, so you'll get psi e prime, psi e double prime. This value is 0. Why this integral is 0? Actually this is 0, this integral is 0, therefore this overall integral is 0. Now what is the reason for this integral is 0? Why? this integral, that is psi e prime, psi e double prime, is equal to 0. Why? The reason is that, see, the wave function psi e prime, that is the wave function for the excited electronic state, and this is wave function for the ground electronic state. Both these wave functions are eigenfunctions of the same Hamiltonian operator. That is, I'll take the electronic Hamiltonian operator. If I apply this electronic operator to the ground electronic state wave function, I'll get the ground state energy and the same wave function psi e double prime. So that means this wave function, right, is an eigenfunction of the electronic Hamiltonian. You take the same electronic Hamiltonian operator, okay, you take the same electronic Hamiltonian operator and apply this operator to the excited electronic state wave function. You will get the same wave function multiplied by a constant, that is nothing but energy of the excited electronic state. See, what does this indicate? These two equations indicates that psi e prime and psi e double prime and psi e single prime, that is electronic wave function for the ground state and electronic wave function for the excited state, both these wave functions are eigenfunctions of the same Hamiltonian operator. They are eigenfunctions of the same Hamiltonian operator, and since the energy values are different, okay, you know very well, ground state energy is low, excited state energy is high. So since these two energies are different, E prime is not equal to E double prime is not equal to E prime. Therefore, the two wave functions, okay, I said these two wave functions are eigenfunctions of the same operator, right? Therefore, since the eigenvalues are different, the two wave functions must be orthogonal. So therefore, psi e double prime and psi e single prime must be orthogonal. Since the two wave functions are eigenfunctions of same electronic Hamiltonian operator, okay, they must be orthogonal. Since they are orthogonal, the integral, right, that is psi e prime, right, psi e double prime, this integral must be 0. Okay, yeah, so this is a very important point, keep this in mind. Why see why this integral is 0, right? The reason is these two wave functions are the eigenfunctions of the same electronic Hamiltonian operator, right? Since they have different energy eigenvalue, they must be orthogonal to each other. Okay, they are orthogonal functions. Since they are orthogonal functions, right, this integral should be equal to 0. Okay, then the next one, the second integral, that is psi v prime and psi v double prime, this integral is not equal to 0. Why? Why this integral is not equal to 0? What's the reason? You know very well, v prime, what is v prime? V prime is the vibrational state associated with the, or vibrational state associated with the excited electronic state. Okay, and v double prime is the vibrational state associated with ground electronic state. Okay, so here you must keep this in mind, that the ground electronic state, internuclear distance for the ground electronic state, and the internuclear distance, equilibrium internuclear distance, okay, equilibrium internuclear distance for the ground electronic state and equilibrium internuclear distance for the excited electronic states, okay, they are not equal for many cases. Okay, or we can say generally it is not equal. if the equilibrium internal conditions are not equal, right, we can say that bond order associated with the ground electronic state and bond order associated with the excited electronic states are not equal. Okay, they are also not equal. Since bond orders are not equal, the corresponding force constant for the ground electronic state and force constant for the excited electronic state of the molecule, they are also not equal. Right? Since force constant, this K represents force constant. Okay, force constant. So force constant of the bond in the ground state and excited state are not equal. Since force constant are not equal, and you know very well, under the assumption of simple harmonic oscillation, very specifically I'll consider the simplest case, that is one-dimensional simple harmonic oscillator. If we assume the vibration as one-dimensional simple harmonic oscillator, okay, then if force constant, you know very well, potential energy depends on force constant, right? Kx square by 2, where K is called force constant, right? So since this is force constant for the ground electronic state, right, and here you'll get force constant for the excited electronic state, right? Since these two are not same, so potential energies are different. Since potential energies are different, the Hamiltonian, the vibrational Hamiltonian for the ground electronic state and the vibrational Hamiltonian for the excited electronic state. Let me put double prime here and single prime here. The vibrational Hamiltonian for the ground electronic state and the vibrational Hamiltonian for the excited electronic states are not same. They are different. Okay, they are not same. So therefore, listen, the wave function, that is psi v double prime, that is ground state vibrational wave function, okay, or wave function associated with, psi v double prime, wave functions associated with the vibrational wave function associated with the ground electronic state. This is an eigenfunction for the vibrational Hamiltonian correspond to the ground electronic state. So if I apply this Hamiltonian operator to this function, yes, I will get the same function multiplied by the corresponding vibrational energy of the ground state, right? Similarly, if I take this excited state vibrational wave function, that is vibrational wave function correspond to excited electronic state, okay, this wave function is an eigenfunction for the vibrational Hamiltonian of the excited electronic state. So if I apply, right, this Hamiltonian to this function, I will get the same function, single prime, this is double prime, okay, single prime into the vibrational energy V prime, vibrational energy for V prime associated with the excited electronic state. Okay, so this function is an eigenfunction of vibrational Hamiltonian operator of the ground state. This function is an eigenfunction of vibrational Hamiltonian of the excited state. Since these two are not equal, okay, so these two eigenfunctions, they are eigenfunctions of different Hamiltonian operator. Okay, they are eigenfunctions of different Hamiltonian operator. Therefore, even the energies are different, these wave functions need not be orthogonal functions. Okay, so psi v double prime and psi v single prime are not orthogonal functions. Therefore, this integral, that is psi v prime psi v double prime, this integral is not equal to 0. We call this integral as overlap integral. Since it is it involves vibrational wave function, it is called vibrational overlap integral. Vibrational overlap integral. Okay, and this overlap can occur between any any vibrational state of the ground electronic level and any vibrational state of the exit electronic level. So there is no there is no restriction on that. Therefore this results into an important condition that the change in vibrational quantum number of the ground electronic state delta V, okay, here there is no restriction. There is no restriction. So any vibrational transitions, right, are allowed in an electronic transition. Okay, see what I'm trying to say. Delta V can be 0, plus or 1, right, 1, 2, 3, 4, etc. right, or plus or minus 1, plus or minus 2, plus or minus 3, etc. Plus signs are applicable for absorption spectrum and minus signs are applicable for emission spectrum. There is no restriction on the vibrational changes. Okay, any vibrational transition is allowed, right, as per this data. Okay, so keep this in mind, very very important, right? Yeah. So after this, so we discussed about the important integrals. Okay, now before going to introduce the formal statement of Franck Condon principle, okay, let me just show you how the vibrational wave function, right, the vibrational wave function will appear in different vibrational states associated with an electronic state, associated with a given electronic state. Okay, see what I'm trying to say here is, suppose I'll take the ground electronic state, right? This, let us say this is ground electronic state. In the ground electronic state we have number of vibrational states. Now I am going to represent the vibrational states wave functions, or the wave function, the nature of the wave function in different vibrational states of a given electronic state. Okay, yeah. So in the ground state wave function will appear like this. Okay, the ground state wave function will appear like this, and the first excited state wave function, yes, it will appear in this manner. It will appear in this manner. Okay, it will have a minimum here, then it has a node, then it goes to a maximum, then it decreases. Okay, it becomes 0 outside this region, which we call as classically forbidden region, right? Why the wave function goes out, becomes 0 outside this curve? Because it is due to quantum mechanical tunneling. Okay, you might have heard about that in the harmonic oscillator discussion, okay, which I am not going to discuss here. I am going to just show you the nature of the wave functions in different vibration states. Then the next level wave function will appear like this. Okay, like that we have wave functions in the higher levels, right? So here we have a function which appear like this. Yeah, it goes like this. Okay, so these are all the nature of the vibrational wave functions, right, in a particular electronic state. Okay, in a similar manner, the excited electronic states also have these wave functions, right? They also have the same type of wave functions associated with the different vibrational states of a electronic state, right? So when transition takes place, I have told you in the case of absorption, almost all transition will occur from V equal to 0 state, where V double prime equal to 0 state. Okay, right? And when the transition takes place from V double prime 0 to some V prime state of the exit electronic level, okay, listen, the wave function of ground state should overlap with the wave function of the V prime state of the exit electronic state. If the overlap is maximum, right, then that gives you the most intense line, okay, which we call as the Franck-Condon factor. Okay, yeah, let us discuss that as we go along. Then I also like to show you that how the probability will look like. Okay, here I have given the wave function, nature of the wave function in different vibrational states, right? But how the probability will look like in different vibrational states, right? So let us take this is the ground vibrational state, the first excited, second excited, third excited, like that. We have many states. Okay, yeah. Now in the ground vibrational state, right, the probability will appear like this. Right? So probability is maximum at the center or at the equilibrium internuclear distance, we can say, right? It is maximum at the center, whereas in the first excited vibrational state, okay, the probability will appear like this. Probability is 0 at the middle and probability will appear like this. And we have some probability outside this forbidden region, classically forbidden region. Then if you go to V double prime equal to 2, yes, we have probabilities which appears like this. See, observe this graph carefully, that the probability at the near the curve, near the terminal of the curve, are more or maximum, right, compared to the probability in the middle, right? Similarly, if we go above and above and above, what will happen? Probability, right, will appear maximum at the terminal points, or I can say that classical turning points, right? These points are called, right? These points are called classical turning points, right? Classical turning points. Okay, after this the atom will come back. Similarly here the atom will come back. So that's why it is called classical turning points, right? Listen, what I am trying to say here is, if you go to the higher vibrational levels of a given electronic state, okay, the probability become maximum, right, near the turning point or at the turning point, at the classical turning point. So probability is maximum at the classical turning point. Keep this in mind, right? You'll have maximum probability if you go to higher vibration levels. Yes, it actually matches with the classical argument, right? When we say in a classical manner, when a molecule vibrate, okay, the atom spends more time at the turning points. Okay, so probability of finding the atom will be more at the turning points, right? It's the same result we get even from the quantum mechanical approach, right? But at the ground vibrational state, probability is maximum at the middle. As we go above and above and above, then the probability slowly shift towards the turning points. So the probability of finding the particle is maximum at the turning point in the higher vibrational levels. Okay, so this is the point I like to say here, right? Yeah, keep this in mind. Now let me introduce what is called the Franck-Condon principle. What is the statement? The formal statement of Franck-Condon principle. Franck-Condon principle. What does this principle say, sir? Listen, an electronic transition takes place so rapidly. An electronic transition takes place so rapidly that a vibrating molecule does not change its internuclear distance appreciably during the transition. Okay, it's a very, very important one. An electronic transition takes place so rapidly that a vibrating molecule does not change its internuclear distance appreciably during the transition. Okay, so this statement very clearly says that the transition from ground electronic state to exit electronic state will occur, right? See, suppose I'll take a ground electronic state having some internuclear distance, equilibrium internuclear distance, and assume that I have another electronic state having some different internuclear equilibrium distance. So equilibrium internuclear distance are not same, but when transition takes place, okay, so suppose assume that I have number of vibrational states associated with the exit electronic state. If transition takes place, transition never goes like this. Okay, if it goes like this, what happens? The internuclear distance changes, right? But the electronic transitions are so fast, okay, during that time interval, right, the molecule cannot or it does not change its internuclear distance appreciably, right? So what I'm trying to say is that the transition always occur in a vertical manner, right? So this is what Franck-Condon principle says that, okay, when an electronic transition takes place from one electronic state to another electronic state, right, the electronic transitions are very fast compared to the change in the internuclear distance, or compared to the vibrational transition. Compared to the change in the internuclear distance, right? So before changing the internuclear distance, the transition will occur because the transition is very, very fast. So we always represent electronic transition, right, in the potential energy curve with a vertical line, right, because the transition is very fast. So in the initial point and the final point, internuclear distance are almost same or same. Okay, almost same or same. Okay, because the vibrational vibrating molecule, right, cannot change the internuclear distance, right, within that fraction of time, right? Usually, you know very well, the absorption takes place in 10 power minus 15 seconds. It is very, very small, right? So, and vibrational motions will occur with a lesser time, roughly 10 power minus 6, like that. Okay, so this occurs in a very fast manner. So the transitions are vertical transitions, right, according to Franck-Condon principle. See, the vertical word that I'm using based on the potential energy diagram. Okay, based on potential energy diagram, the transitions are supposed to be represented in a vertical manner. Okay, yeah, this is what we call as Franck-Condon principle. Now, if it is so, if Franck-Condon principle is applicable, right, if Franck-Condon principle operates, okay, in the transition, then what will happen? Listen, see, there will be small probability of transition from 0 to 0. There will be some probability of transition to 0 to 1, 0 to 2, etc. Okay, but which transition will give most intense line? So intensity of these vibrational transitions in an electronic transition. Okay, so what I'm trying to say, so what decides the intensity of vibrational transitions? Okay, intensities of of vibrational, right, intensities of vibrational transitions in an electronic transition, right, in an electronic transition. So when an electronic transition takes place, many numbers of vibrational transition will occur, that I told you before. Now, many vibrational transitions will occur. Now the question is, which transition, right, among many vibrational transition, which transition will appear with the maximum intensity, right? How to get that? Yes, this depends on, this is actually decided by, okay, this is actually decided by the Franck-Condon factor. Okay, yeah. So according to Franck-Condon, what is Franck-Condon factor? See, according to Franck-Condon principle, vertical transitions are the only transition possible. Therefore, the intensity of the vibrational transitions, okay, or vibrational lines in an electronic transition depends on the Franck-Condon factor. It not only depends on Franck-Condon factor, it also depends on other things, but Franck-Condon factor is the one which depends upon the molecular properties, right, or vibrational states. So let us take this one. So Franck-Condon factor. What is Franck-Condon factor? Okay, last class I told you the Franck-Condon factor is represented by S. This is the usual notation, right, which is given as, it is the square of the overlap integral, okay, vibrational overlap integral. So this is vibrational overlap integral, psi v prime, psi v double prime, right? This is the overlap integral. Take the square of this. Take the square of this. Okay, right. Take the square of this vibrational overlap integral. That gives you the Franck-Condon factor. And intensity of the transition V double prime to V single prime, intensity of the transition in absorption, right, it is directly proportional to the Franck-Condon factor. It's directly proportional to the Franck-Condon factor, right? So if the Franck-Condon factor is more, you'll get maximum intensity, you'll get more intensity of the particular vibrational transition in an electronic transition. Okay, now this Franck-Condon factor value will be maximum if the overlap integral is maximum. Okay, so the overlap of the ground state vibrational wave function and the excited state vibrational wave function decides this Franck-Condon factor. And in the case of absorption, right, in absorption I told you almost all molecule present in the ground vibrational state. So in the case of absorption, the Franck-Condon factor, right, actually depends on psi v prime, because this is always the ground state of the ground vibrational state of the ground electronic state. Okay, so it depends on the value of psi v prime. Okay, so when transition takes place, right, which vibrational state of the excited electronic state overlap maximum with the ground vibrational state of the ground electronic state, that actually decides the intensity of the transition. Okay, so we'll discuss different cases here, how depending upon the molecule, right, you'll get different vibrational lines will produce maximum intensity. Okay, so how these lines appear, we will discuss now. Okay, so first let me take a particular molecule where there won't be a big change in the internuclear distance. Okay, so let us take the first case. Okay, this is case 1. case 1, where internuclear distance of the ground electronic state and the internuclear distance of the exit electronic state, okay, let it be approximately equal. Okay, if it is approximately equal, I have told you already, it may be due to transition from bonding molecular orbital to bonding molecular orbital, or anti-bonding molecular orbital to another anti-bonding molecular orbital. Okay, usually the internuclear distance will not change appreciably. Okay, if you take the equilibrium internuclear distance for the ground electronic state and the equilibrium internuclear distance for the exit electronic state, okay, are roughly equal if transition occurs from bonding molecular orbital to bonding molecular orbital or anti-bonding to anti-bonding, right? This is for information sake I'm saying. Now suppose if I take the vibrational states having almost same internuclear distance. Okay, so here I have internal energy, here I have internuclear distance. Okay, let me draw a line here so that it will be comfortable to draw. Okay, so let us assume that this is the ground state wave function, potential curve, and this is the excited state potential curve. Excited state potential curve. Okay, this is the stable ground electronic state and this is stable excited electronic state. Okay, now the internuclear distance, right, for the ground electronic state and the excited electronic states, okay, are almost equal. If it is equal, then which transition will appear with the maximum intensity? You know very well, from the ground state always transition appears from the ground vibrational state. Okay, and probability of ground vibrational state is maximum at the middle, right? In the excited vibrational state, if you take, okay, let me draw here. Yeah, this is the ground vibrational state, this is the next vibrational state, this is next vibrational state. Like that we have many vibrational state. So in the ground vibrational state also probability is maximum at the middle, right? Now since the internuclear distance are same, almost the same, so the transition occurs in a vertical manner according to Franck-Condon principle. So this implies that if internuclear distance are almost equal, then the transition from 0 to 0 will give you the maximum intensity, right? Whereas 0 to 1, suppose if you take 0 to 1, see, probability for the first excited vibrational state in the excited electronic state, right, the probability is 0 at the middle, but transition occurs from the middle, therefore it meets the point where probability is minimum in the first vibrational state. Similarly in the second vibrational state, if I say second excited vibrational state, third excited vibration, like that. So the intensity will be maximum for 0 to 0 transition, okay, when the internuclear distance are roughly equal. This is what scientists have observed in the case of oxygen molecule. Right, in the case of oxygen molecule, the electronic transition will produce, or the absorption spectrum. The absorption spectrum will give you intensities which appear like this. Let me show that here. So when you plot, this is the spectrum for the electronic absorption spectra of oxygen molecule. Okay, we plot intensity in y-axis and let us plot wave number in x-axis. Okay, wave number or frequency or wavelength, anything you can plot. Okay, here I am going to plot with wave number, and you know very well wave number here, as per this diagram, wave number increases from left to right, and you know energy is directly proportional to wave number. If energy required for transition is low, wave number also must be low. So here in this diagram it is very clear that 0 to 0 transition will have the lowest energy for the transition. Then 0 to 1 will require somewhat higher energy, 0 to 2 requires somewhat higher energy. So as the energy increases, wave number also will increase. Therefore the first line that appears, right, in the spectrum is due to the 0 to 0 transition. Okay, and here that transition has the maximum intensity because the overlap will be maximum for the 0 state of the ground electronic state and 0 vibrational state of the exit electronic state. So because the probability is maximum in the transition line. Okay, so I can say that you'll get a maximum, right? Then as we go to the next lines, the next lines will appear with the minimum or degrading intensities like this. Okay, this is how the spectrum. Suppose if we take a gas phase spectrum, okay, in the gaseous state, right, you can see you can see the lines actually. Okay, actually these are not lines, they are also small peaks. Okay, but for understanding purpose, I told you that we have assumed the transitions are rotationless states. Okay, transition occurs between rotationless states. So the rotational transitions are supposed to be inside. Okay, let us not worry about that now. So each line here gives you what is called vibrational transition lines. Okay, the first line is due to 0 to 0 transition, ground vibrational state to exit vibrational state. The second line is due to 0 to 1 transition, 1 0, right? Then this is 2 0, this is 3 0, etc. Okay, it is very clear that this transition acts. Okay, the first line will appear with the maximum intensity, and intensity decreases as we go to the higher wave numbers. Okay, this type of spectrum, right? This type of spectrum will appear if the internuclear distance of the ground vibrational electronic state and the exit electronic state are approximately equal. Okay, see in gas phase you can see these fine lines. Okay, we call this group of lines as the vibrational core structure. Okay, or also called Franck-Condon envelope. It is also called Franck-Condon envelope, right? Yeah, and if you take a spectrum in solvent, okay, if you take a spectrum of the molecule in a particular solvent, okay, then collisional interactions will be there, solvent collisional interactions. So because of that, okay, you cannot see these lines. Actually it will appear, okay, it will appear in this manner, right? It will appear in this manner. Okay, so it is very clear that if spectrum appears like a band, right, it is maybe due to the poor resolution spectrum, or maybe due to some solvent interactions. Okay, but in gas phase as well as with a high resolution spectrum, right, you can get these lines. Okay, so this is very, very important, keep this in mind. So this is for case 1, right? I stop here. For the remaining cases, that is case 2, case 3, etc., we'll discuss in the next lecture. Thank you.